For more than a century, humans have assumed leaving the solar system is just a matter of time. Bigger rockets, better engines, more advanced technology. But the deeper you look, the more disturbing the truth becomes, because this may be one of those dreams that is not just difficult, but effectively impossible for human beings. And once you see the scale of what space actually demands, that idea stops sounding extreme and starts sounding unavoidable. But before we continue, please subscribe to the channel to give your support. Let's continue. You think space should make travel easier because there is no air in the way, no drag, no friction, nothing to slow a ship down. That sounds reasonable, and that is exactly why this subject fools people so easily. The vacuum of space helps in one very narrow sense. Yes, you do not waste energy pushing through air, but the same emptiness also removes everything that helps you survive. There is no oxygen out there, no fuel stations, no spare parts, no pressure, no warmth, no natural radiation shield, no food source, no rescue, and no environment that supports a human body in any way. Once you leave Earth, every single thing that keeps you alive has to travel with you. Every meter per second of speed, every kilogram of shielding, every liter of water, every watt of power, every calorie of food, every medicine, every backup system, every tool, every repair material. You either bring it or you do without it. That is the first mistake people make. They hear vacuum and think freedom. In reality, vacuum means total dependence on your own machine. Space does not fight you with air resistance, but it also does not help you with anything else. On Earth, the planet is doing most of the work all the time, and you barely notice it. Earth gives you breathable air, stable pressure, gravity, temperature buffering, a magnetic field, an atmosphere that blocks a huge amount of harmful radiation, and a giant biosphere that constantly recycles what life needs. In deep space, none of that exists. A spacecraft is not just a vehicle, it's a tiny life support bubble that must replace part of a planet. That is already hard for weeks or months. For years or decades, it becomes a completely different level of difficulty. Then the scale of the solar system makes the situation worse. People say the solar system is big, but that word is too weak. It's not just big, it's so large that normal human intuition stops working. Earth orbits the Sun at about 150 million kilometers, around 93 million miles. That already feels huge. Neptune, much farther out, is roughly 4.5 billion kilometers from the Sun, about 2.8 billion miles. Most people hear that and think that must be close to the edge. It is not. The heliopause, the region where the solar wind weakens and interstellar space begins to dominate, is around 120 times farther from the Sun than Earth is. That's about 18 billion kilometers, around 11 billion miles. And even that is not the full outer reach of the Sun's gravitational influence. This is why Voyager 1 matters so much in this discussion. Voyager 1 launched in 1977. It's the farthest human-made object from Earth and one of the fastest spacecraft ever sent out of the solar system. It crossed the heliopause in 2012. That means it took more than 35 years just to reach the edge of the Sun's immediate bubble. Not another star, not even a nearby destination outside our stellar neighborhood. Just the edge of the Sun's front yard. That single fact should reset how you think about all of this. Our best real example of outward travel took decades to get to the boundary of local interstellar space, and it wasn't carrying people, life support, or a return plan. Then your sense of speed breaks too. In everyday life, speed means something very different. A car at highway speed feels fast. A jet feels extremely fast. A rocket feels almost unreal. Voyager 1 travels at about 17 kilometers per second, nearly 61,000 kilometers per hour, or about 38,000 miles per hour. On human scales, that's an extraordinary speed. It's far beyond anything a person normally experiences. But interstellar distance is so extreme that even this speed is not remotely enough for human travel. Proxima Centauri, the nearest star to the Sun, is about 4.24 light-years away. In ordinary distance units, that's around 40 trillion kilometers, or about 25 trillion miles. At Voyager 1 speed, a trip there would take more than 70,000 years. That number is so large that people often stop processing it. More than 70,000 years is longer than recorded history. It's longer than agriculture, longer than cities, longer than written language. If you launch the mission at that timescale, the ship would outlast governments, cultures, languages, and probably entire civilizations. The basic point is simple. Something can be extremely fast by human standards and still be functionally useless for interstellar travel. This is where a second major misunderstanding appears. People often think the solution is just one breakthrough away. Build a better engine, use better fuel, make a bigger ship. But the problem is not one missing invention. The problem is that every part of the mission multiplies the others. You need high speed, but high speed needs huge energy. You need huge energy, but energy systems add mass. More mass makes propulsion harder. Harder propulsion usually means more fuel or more powerful engines, which adds more mass again. Then you still need shielding from radiation, you still need water, oxygen, food waste recycling, power generation, heat management, medical capability, and repair systems. You still need a structure that can survive for extreme lengths of time without outside support. That is why this doesn't behave like a normal engineering project. Usually, if something is difficult, you can isolate the hard part and improve it. Here, the hard parts are connected. Solve one and two others grow larger. Make the ship safer for humans and it gets heavier. Make it heavier and it becomes harder to accelerate. Increase the power to accelerate it and now you have more heat, more complexity, and more failure points. Try to shorten the trip time and the energy demand rises dramatically. Add more supplies for the crew and the propulsion burden rises again. This is not one obstacle. It's a stack of linked obstacles that reinforce each other. And the deeper point is even more uncomfortable. This is not mainly a story about weak technology. It's a story about scale. Human beings are built for a planet, not for interstellar distance. Your body needs a narrow range of conditions. Your life has a limited length. Your mind measures time in days and years, not centuries or millennia. Your machines wear out. Your societies change. The distances between stars are so extreme that they expose every limit at once: biological limits, engineering limits, energy limits, and civilizational limits. That is why the phrase "leave the solar system" sounds much simpler than it really is. It sounds like one long trip outward. In practice, it means carrying part of Earth with you into an environment that gives you nothing, across distances so large that your best existing spacecraft barely make visible progress, while solving a chain of problems that get worse as soon as you try to solve them. And once that becomes clear, the tension rises immediately, because the first major barrier is not deep space, and it's not even the distance to another star. The first major barrier is much closer than that. It's the fact that before you can leave the solar system at all, you first have to escape Earth, and Earth does not let go easily. You are not blocked by the stars first. You are blocked by Earth. That is the part people skip past too fast. They talk about deep space, other star systems, advanced engines, maybe even life on exoplanets, but all of that comes later. Before any of it matters, you have to do something that is already brutally hard. You have to get off this planet. And Earth does not let go gently. Earth escape velocity is about 11.2 kilometers per second, around 25,000 miles per hour. That is not a comfortable travel speed, and it is not some bonus target for a fast mission. That is the minimum speed you need to break free from Earth's gravity if you are not planning to keep firing your engines forever. If you are below that, Earth keeps you. And even that number can be misleading because people hear escape velocity and think that is the whole challenge. It is not. Reaching low Earth orbit already takes an enormous amount of energy. Orbit is not a halfway point in any practical sense. It sounds like you just go up a little, then the rest is easy. But in energy terms, getting to orbit is most of the fight. You are not just going upward, you are building up enough speed sideways that you keep missing the planet as you fall. That is why a spacecraft in orbit is not floating because gravity has disappeared. It is falling around Earth fast enough to stay up. That means the first stage of any mission is already extreme. You are lifting a machine, its structure, its engines, its fuel, its payload, and all the fuel needed to lift the rest of that fuel out of a deep gravity well. That is why rockets do not look elegant when they launch. They look oversized, stacked, and wasteful, because they are fighting physics in the most expensive way possible. Almost everything you see on a launch pad is not payload. It is the system needed to push a much smaller amount of useful mass out of Earth's grip. And that takes you to one of the most unforgiving rules in engineering, the rocket equation. You do not need the math written out to understand the problem. The logic is enough. If you want more speed, you need to throw propellant out the back faster or in larger amounts. But propellant has mass, so if you want to carry more propellant, your vehicle gets heavier. And if your vehicle gets heavier, you now need even more propellant to accelerate that extra propellant. Then that extra propellant also has to be accelerated, which means you need more again. This is why rockets scale so badly. Each increase in desired speed makes the fuel problem much worse, not a little worse. That is why launch vehicles start as giant towers and end as tiny payloads. A huge amount of the rocket exists only to get rid of the rest of the rocket. Stages burn, separate, and fall away because carrying empty tanks and dead engines would make the problem even worse. By the time the useful part of the mission is actually on its way, most of the original machine is gone. The physics is not flexible here. It does not care how badly you want a bigger payload or a faster trajectory. If you want more velocity using ordinary rockets, the vehicle turns into a flying fuel tank very quickly. And this is where people often say, fine, then we just need better rockets. But better by how much? Chemical rockets are already close to the practical limits of what chemistry gives you. They're powerful enough for launch because chemical reactions can release energy fast, which is exactly what you need to get off Earth. But they are terrible for interstellar ambition. Their exhaust speeds are far too low. In simple terms, chemical propulsion can throw mass out the back at only a few kilometers per second. That is useful for launching spacecraft, changing orbits, sending probes to planets, and doing serious work inside the solar system. It is nowhere near enough for sending humans to another star on anything like human timescale. That is the key point. Chemical rockets are not bad technology. They are the right technology for the wrong scale. They work for missions measured in months or years inside one stellar system. They do not work for trying to cross distances measured in light years. Even if you improved them, even if you built larger ones, even if you launched in pieces and assembled things in orbit, you still run into the same wall. The amount of propellant needed becomes absurd, then impossible. Then people move to the next idea: use nuclear propulsion. And yes, nuclear thermal propulsion could beat chemical rockets by a significant margin. It could give you better efficiency, better exhaust speed, better mission flexibility. That matters. It could help with travel inside the solar system, but it still doesn't get you close to what humans would need for interstellar travel. It's an improvement inside the same overall prison, not a jailbreak. So then another hopeful argument appears. Gravity assist. Use planets, use their motion, use the solar system itself to help you. And that part is real. It's smart, and it works. Voyager used gravity assist from Jupiter and Saturn. That is one of the greatest mission design achievements in spaceflight. You can approach a moving planet in the right way and leave with more speed, effectively taking a tiny piece of that planet's orbital momentum. It's a brilliant trick, and it lets robotic probes do things that would otherwise be far harder. But gravity assists are not magic. They don't create unlimited energy, and they don't let you ignore the rest of the problem. They depend on the planets being in the right places at the right times. They depend on specific trajectories and specific mission design choices. And the amount of speed you gain, while impressive by normal spaceflight standards, is still tiny compared to what a human interstellar ship would need. A gravity assist can help a probe move faster through the solar system. It does not get a human habitat anywhere near a meaningful fraction of light speed. That difference matters because people keep mixing two completely different categories. A robotic probe can be small, stripped down, and disposable. A human vessel has to be much larger, much heavier, far more reliable, and packed with systems that don't help propulsion at all. So even if gravity assists are useful, they are useful on top of a mass problem that is already getting worse. And that leads to the most important point in this whole section. The first prison is local. Deep space is not the first thing that stops you. Your home planet is. Before the cosmic problem even begins, Earth forces you to spend astonishing amounts of energy just to step outside. Every dream of a sleek interstellar ship hides this ugly reality at the beginning. It has to start as a launch problem. And launch problems are violent, expensive, mass-sensitive, and unforgiving. The image people carry in their heads is usually a clean starship moving quietly through the dark. The real beginning looks nothing like that. It starts with a controlled explosion under a stack of fuel trying to throw a comparatively tiny payload out of one planet's gravity well. And right there, before the journey to another star even enters the conversation, the numbers are already bad. Because if the best launch systems your civilization can build can barely send a few dozen tons onto serious escape paths, then the next question gets much harder, much darker, and much more serious. How do you deal with the fact that even our fastest probes are still almost standing still on a cosmic scale? Our fastest spacecraft are not fast in the way this problem needs. That sounds wrong at first because if you look at a mission like Voyager 1, the numbers seem incredible. Voyager 1 is moving at roughly 17 kilometers per second, about 10.5 miles per second. That is around 61,000 kilometers per hour, or roughly 38,000 miles per hour. On any human scale, that is extreme. A vehicle moving that fast would cross the continental United States in a short time if it can move through air, which it cannot. So your brain hears that number and says, that's enough. That has to count as real deep space speed. But this is exactly where scale breaks your intuition again. Space travel inside the solar system and travel between stars are not separated by a small difference. They are separated by a different category of distance. In terms of light speed, Voyager 1 is moving at only about 0.0057% of light speed. That is not just slow compared to science fiction. It's slow in a way that makes interstellar human travel basically non-functional. When you convert the number into the scale that actually matters, the feeling of speed disappears. And that same lesson showed up again with New Horizons. New Horizons was one of the fastest probes ever launched from Earth. It left in 2006, got a gravity assist from Jupiter, and headed for Pluto at a speed that was impressive by real mission standards. It reached Pluto in 2015. That was an extraordinary mission. It gave us the first close-up look at a dwarf planet we had never really seen properly before. And scientifically, it was a huge success. But look at what the mission actually tells you about scale. It still took about 9.5 years to reach Pluto. Not another star, not interstellar space, not even the outermost true edge of the sun's domain. Just Pluto, a distant object inside our own solar system. That is the point people keep missing. A mission can be a major triumph and still prove that human interstellar travel is nowhere close. New Horizons did not fail. It proved the problem is bigger than most people think. And then the scale gets worse because Pluto is not the edge of anything important in this discussion. Beyond the planets, beyond the Kuiper Belt, there is the Oort cloud, a huge reservoir of icy bodies that may extend from roughly 2,000 astronomical units out to perhaps 100,000 astronomical units from the Sun, possibly even farther, depending on how you define its boundaries. 1 astronomical unit is the average distance between Earth and the Sun, about 150 million kilometers, or 93 million miles. At the far end, 100,000 astronomical units is around 1.5 light years. That means something very important. Long before you get to another star, you may still be moving through the outer debris region associated with your own star. In other words, the solar system is not just the neat diagram you saw in school. Sun in the middle, planets in a tidy row, then done. That picture is useful for teaching. but physically it is incomplete. The sun's real domain is much larger and much less tidy. It is a vast gravitational region with objects scattered at enormous distances. So when people casually say leave the solar system, they are usually thinking about passing Neptune or maybe crossing the heliopause. But if you are talking about getting fully beyond the sun's extended influence on the architecture of the system, the scale becomes even more extreme. That destroys human mission timelines. A human being can think in years, maybe decades. A civilization can plan across generations if it is unusually stable. But once the distances are large enough that even the outer structure of your own stellar system takes absurd amounts of time to cross, the whole idea starts to change. You are no longer talking about travel in the normal sense. You are talking about persistence across spans of time that human institutions do not handle well. And this is where people often point at the probes and say, but we already sent things out there. We already proved it. No, we proved that machines can survive long trips. That is a real achievement, but it is not the same claim at all. A robotic probe does not need oxygen. It does not need food. It does not need sleep. It does not need exercise to stop its bones and muscles from breaking down. It does not need a doctor. It does not get cancer anxiety. It does not suffer loneliness. It does not need children, education, social order, or a legal system. It does not need an artificial ecosystem running perfectly for generations. That difference is not a detail. It is the whole argument. Voyager lasting for decades on radioisotope power tells you a hardened machine can keep going in deep space. That is impressive and useful. But it tells you almost nothing about whether a ship carrying people could do the same thing. The gap between a probe and a human mission is not just payload size, it's the difference between transporting hardware and transporting a living society. And once you compare those mission types honestly, the nearest star becomes a much harsher number. Proxima Centauri is about 4.24 light-years away, roughly 40 trillion kilometers, or about 25 trillion miles. At Voyager 1 speed, the travel time would be on the order of tens of thousands of years. That phrase is so large that people often stop taking it seriously, so it helps to say what it actually means. It means the mission would last longer than recorded history. It means the launch civilization could disappear while the ship was still barely on its way. It means languages on Earth could change beyond recognition. It means systems could collapse and reappear in forms nobody aboard the ship would understand. It means whole cultures, maybe even species, could vanish before the mission ends. And once you say it that way, the question changes completely. It stops being, can a human ship go that far? In a narrow mechanical sense, you could always keep something drifting outward. The real question is whether any human-made system can stay functional for that long inside a closed machine. Can life support stay stable? Can knowledge survive? Can repairs continue? Can medicine continue? Can the purpose of the mission survive longer than civilizations usually survive on Earth? That is the devastating comparison. Our fastest probes feel fast because your brain is built for short distances in short times. On interstellar scales, they are barely moving. And that means the problem is no longer just about leaving Earth or even leaving the solar system. The problem becomes much worse than that, because if current high-end spacecraft are still effectively crawling, then the next step is brutal. The speed humans would actually need starts pushing the energy cost into a range that breaks the entire budget. The speed humans would need is so high that the energy cost stops sounding like a vehicle problem and starts sounding like a civilization problem. That is the next hard step in this argument. It is not enough to say the stars are far away. Distance by itself does not kill the idea. The real damage happens when you ask a more practical question. How fast would a human ship actually need to go for the trip to mean anything to the people on board? If you want a crew to reach even the nearest stars in something like 40 to 80 years, which is already pushing the edge of a human lifetime, then you are no longer talking about slightly better spacecraft. You are talking about velocities that are a serious fraction of the speed of light. 10% of light speed is about 30,000 kilometers per second, around 18,600 miles per second.
Put that next to Voyager 1 at roughly 17 kilometers per second, and the comparison becomes brutal. This is not a small upgrade. It is not even a large upgrade in the normal sense. It's a jump by a factor of roughly 1700. That should immediately tell you the problem is not just engineering improvement. It's a scale break. It's the difference between the fastest thing humanity has actually sent outward and the kind of speed interstellar human travel would need just to become barely plausible within one lifetime. And once velocity gets that high, energy becomes the main enemy. The rule here is simple, and it is devastating. The energy needed to move something rises with the square of its speed. So if you double the speed, the energy does not merely double, it goes up by 4 times. If you increase speed by 10, energy goes up by 100. Increase speed by 1,000, and now you're talking about 1,000,000 times more energy. That is why people underestimate this so badly. Human intuition expects costs to rise in a roughly straight line. Space does not work that way once the speeds get extreme. Now, apply that to a crude ship. Even a small human interstellar vessel would not actually be small. If you say 1,000 metric tons, about 1,100 US tons, that already sounds massive. But for a human deep space vehicle, it is almost conservative. By the time you include structure, life support, shielding, supplies, power systems, and redundancy, you are talking about something far larger than a typical spacecraft. But even with that relatively restrained number, getting that ship up to 10% of light speed means kinetic energy on the order of 450 quintillion joules. That number is too abstract by itself, so translate it into meaning. It is comparable to a substantial fraction of what human civilization uses in total energy over an entire year. And that is just the raw kinetic energy of the ship once it is moving. That is not the energy your propulsion system must produce in practice. Real engines are not perfectly efficient. Real systems lose energy as heat. Real missions need power conversion, control systems, shielding, structure, and probably huge supporting infrastructure. So the actual cost is much worse than the already terrible number. And that still isn't the full mission. Because a human mission is not a bullet fired once into the dark. If you want to arrive in another star system and do anything useful, you have to slow down too. If you spend immense energy getting the ship to high speed and then cannot stop, you do not really have a mission, you have a flyby. You race through the target system and keep going. So now the basic picture gets even uglier. You need energy to accelerate, and then you need more energy to decelerate. In broad practical terms, the problem roughly doubles before you even start counting inefficiencies and fuel penalties. That brings in the next part of the trap, the fuel problem. If your ship carries its own propellant, then things get ugly very fast. To speed up, you need to throw mass out the back. To slow down later, you need another supply of propellant for braking. But that braking propellant has to be carried during the first half of the trip, which means you need extra propellant at the start just to accelerate the propellant that you plan to use later. And that extra propellant itself adds mass too. This is how mass ratios spiral out of control. The vehicle gets dominated by the burden of carrying fuel for future burns, and then carrying fuel to carry that fuel. That is why chemical propulsion is not just weak for this task, it is hopeless. Chemical rockets are fine for launch and useful missions inside the solar system, but for interstellar human travel, their exhaust speeds are far too low. The fuel mass would become absurd long before you reached anything close to the necessary velocity. Nuclear propulsion can improve the picture, yes, but not enough. It helps, but it does not rescue the concept. Fusion gets discussed a lot because, in theory, it offers much higher energy density, but practical fusion propulsion for a real ship remains unproven. Antimatter looks powerful on paper too, but the reality is much harsher. We produce tiny amounts of it at enormous cost, and storing it safely is an extreme challenge. You do not solve one impossible problem by assuming another impossible technology will be waiting for you. And this is where a lot of discussions become misleading. Someone will say, correctly, that physics does not completely forbid high-speed interstellar travel. Strictly speaking, yes, there is no law of nature that says matter can never move from one star to another, but that statement is much less impressive than it sounds. Physics does not forbid many things that are still far beyond what a real civilization can actually do. The real question is not whether the universe permits it in principle. The real question is whether a species like ours can build it, power it, test it, pay for it, maintain it, and launch it safely. That changes the conversation immediately. Now you're not just talking about an engine. You're talking about mining, manufacturing, power generation, material science, long-term maintenance, launch infrastructure, mission planning, agreement, economic commitment, and industrial capacity on an enormous scale. And all of that would be directed toward a machine more complicated than any habitat ever built, for a mission whose full return might not be seen for decades, generations, or longer. That is not just a hard project. That is a civilization-scale gamble with almost no historical comparison. And every time you try to make the ship more realistic, the energy problem gets worse. Add better shielding, mass rises. Add larger life support margins, mass rises. Add medical capability, spare parts, a more stable habitat, redundancy, repair tools, radiation shelters, stronger structure, better protection from impacts, more food reserves, more water, more people to keep the mission socially stable. Every one of those choices adds mass, and every increase in mass drives the energy demand upward again. So the design doesn't settle into a workable middle ground. It keeps curving upward into a wall. That is the trap taking full shape. To make interstellar travel fast enough for humans, you need enormous speed. Enormous speed needs enormous energy. Enormous energy systems add mass and complexity. Mass and complexity then demand even more energy. The stars are not just far away. The cost of reaching them with living passengers rises so fast that it pushes the whole idea towards something close to practical impossibility. And once the energy budget starts breaking under its own scale, the next part gets even worse, because even if you somehow had the propulsion, even if you somehow paid the energy cost, you would still have to face a simpler and more disturbing fact. The human body itself is built for Earth, not for deep time inside a machine. The ship does not just have to survive space, your body has to survive it too. And that is where this starts getting much worse. A lot of people talk about interstellar travel like the main challenge is building the machine. Build the engine, build the hull, build the power source, and the rest is just logistics. But a human mission is not just a vehicle problem. It's a biology problem from the first second to the last. Human biology is extremely local. Your body is not general purpose. It's tuned very specifically for Earth. Your bones expect constant load from gravity. Your muscles expect resistance. Your heart and blood vessels expect a certain pressure pattern. Your immune system expects continuous contact with a huge living biosphere. Your sleep cycle expects a 24-hour day. Your lungs, your eyes, your nervous system, your hormones, all of it evolved inside one narrow environment. Take that body and move it into deep space for years, decades, or generations, and the question is no longer whether it is comfortable. The question is whether it remains functional at all. This is not speculation. We already know that even short-term spaceflight changes the human body in serious ways. The body starts adapting to an environment it was never meant to live in, and many of those adaptations are bad for long-term health. Microgravity is one of the clearest examples. People sometimes think weightlessness is just a fun side effect, floating around, doing flips, looking peaceful on camera. In reality, microgravity actively damages the body. On the International Space Station, astronauts lose bone density and muscle mass, even with strict exercise programs. Without countermeasures, bone loss in important weight-bearing areas can reach around 1 to 1.5% per month. That is severe. Muscles shrink because the body stops investing in tissue it does not need as much. Fluids shift upward toward the head because gravity is no longer pulling them down the same way. That fluid shift is linked to vision problems in some astronauts. The cardiovascular system also deconditions because the heart and blood vessels are not working against gravity the way they do on Earth. And that is happening in low Earth orbit, only a few hundred kilometers, a few hundred miles above the planet. The astronauts are still close enough for constant communication. Missions are planned carefully. Medical support exists on the ground. Supplies can be sent up. Emergencies, while still dangerous, happen inside a framework connected to all of Earth's resources, and even under those conditions, the body struggles. So now extend that from months to years, then from years to decades. Then imagine children being born into that environment. The risk is no longer just bone loss or weaker muscles. The risk is that you are trying to build a long-term human life in conditions that keep pushing the body away from normal function. Then the problem gets bigger, because keeping the crew alive is not just about the body itself. It's about the entire support system around the body. Oxygen, water, food, waste recycling, air quality, microbial balance, temperature control, and chemical stability all have to keep working continuously. For a short mission, you can carry a lot with you. For a very long mission, that stops being enough. You need a closed life support system, which means the ship has to keep reprocessing what the crew uses and produces. Water has to be recovered. Air has to be cleaned and recycled. Waste has to be processed. Food has to be grown or produced somehow. Microbes have to stay under control without collapsing the useful parts of the system. That sounds manageable when you say it quickly. It becomes much harder when you remember we have never solved this at anything like interstellar scale. Small closed systems are fragile. A tiny imbalance can grow into a big one if there's no outside correction. Biosphere 2 is a famous example of how difficult ecological closure really is. Oxygen levels dropped. Ecological balances shifted in ways the designers did not fully expect. Human intervention became necessary. And that was on Earth, with full access to outside help, outside air, outside expertise, and emergency intervention whenever needed. A starship would not have that safety net. It would have to remain chemically, biologically, and socially stable on its own for durations far beyond anything we have ever tested. And once you think about life support honestly, medicine becomes even more serious. The phrase medical issue sounds manageable on Earth because Earth has hospitals, specialists, supply chains, labs, and industrial systems behind those words. In deep space, medicine becomes its own world of problems. What happens when someone develops appendicitis, or cancer, or severe depression, or psychosis, or a dangerous infection, or a pregnancy complication, or a surgical emergency, or chronic organ failure caused by long exposure to radiation and stress? You're not calling Earth for rescue. You're not requesting a fast return. You're not waiting for a specialist to fly in. The ship is the hospital, permanently. That means a true human interstellar vehicle cannot just carry bandages, antibiotics, and a smart medical officer. It would need diagnostics, surgical tools, long-term pharmaceutical production or storage, imaging capability, intensive care capability, sterilization systems, spare parts for medical hardware, and people trained across multiple kinds of medicine. It may also need advanced manufacturing because tools break and supplies expire. It may need biological engineering tools if long-duration health problems become unavoidable. Once you keep following that logic, the ship starts turning into something much larger. It begins to look like a tiny civilization with a built-in hospital, lab, workshop, and educational system, all of which must keep functioning without outside support. And then the hardest part appears. This is not just about keeping one crew alive for one mission. If the trip takes longer than one lifetime, then children are born aboard. At that point, the mission changes category completely. It is no longer just transportation. It becomes inheritance. A new generation grows up inside a closed environment they never chose. They don't remember Earth. They don't step outside into weather, landscapes, oceans, forests, or open horizons. Their entire world is machinery, recycled air, limited space, managed systems, and a mission started by dead ancestors. That creates a problem that is not only technical, it's biological, social, and moral at the same time. Can a human lineage remain healthy in that environment? Can children develop normally in artificial gravity, if you even have artificial gravity, or in reduced gravity, or in rotating habitats with their own engineering limits? Can long-term exposure to radiation, isolation, and closed-system living damage fertility, development, or mental health across generations? Can a society remain cooperative under those conditions, or does confinement slowly break it down? This is why the phrase humans in deep space hides so much. It sounds like a transportation issue, but it's really a question about whether human life can be detached from Earth for very long without falling apart. The body is not a passive passenger. It's one of the weakest systems in the mission. The crew doesn't simply ride inside the starship. In a very real sense, the crew is part of the starship and one of its most failure-prone parts. So even if you somehow solve propulsion, even if you somehow solve the energy cost, even if you somehow build a closed habitat that can function for an extreme length of time, another threat is still waiting, one that keeps damaging the body slowly, constantly, and invisibly. Because deep space doesn't have to crush you quickly to destroy the mission, it can just poison you over time. Radiation is one of the clearest reasons a human starship stops looking like a vehicle and starts looking like a slow-motion medical disaster. On Earth, you are protected much more than you usually notice. The atmosphere above you blocks and absorbs a huge amount of harmful radiation. Earth's magnetic field also deflects many charged particles before they ever reach the surface. That protection is so normal that it becomes invisible. You live your whole life under it, so it feels like the default condition of the universe. It is not. It's a special local shield, and outside that shield, the situation changes immediately. Deep space is not peaceful in the way people often picture it. It looks empty, calm, silent, almost harmless. But from a radiation point of view, it's a place where the crew is being hit all the time, not by one dramatic blast every day, but by a continuous background attack. You have galactic cosmic rays coming from outside the solar system, solar energetic particles coming from the sun, and then another layer of danger created when some of those particles strike the spacecraft itself and produce secondary radiation inside the structure. So even the walls meant to protect you can create new problems when high-energy particles slam into them. That matters because this is not just theory. We have measured radiation on real deep space missions. Instruments carried during the Mars Science Levery cruise to Mars showed that exposure during the cruise was already significant, and that was on a mission lasting months, not years. Mars missions are already serious enough that astronaut lifetime exposure becomes an issue. That's for a journey inside our own solar system, over a timescale humans can still manage. Now extend that same basic danger from months to decades, or centuries, and the picture gets much darker. The longer the exposure lasts, the more the damage accumulates. Cancer risk rises. Damage to DNA builds over time. Harm to the central nervous system becomes a concern. Cardiovascular effects matter too. This is not one simple illness with one simple fix. Radiation can affect multiple systems at once, and some of the consequences may show up slowly. That makes it harder, not easier, because the mission can appear functional while the crew is gradually being damaged underneath it. Then the obvious answer shows up. Add shielding. That sounds practical. If radiation is dangerous, put more material between the crew and space. But once again, the answer runs straight into mass. Shielding is heavy, and heavy is deadly to the mission budget. Every extra layer you add makes the vehicle harder to launch, harder to accelerate, harder to decelerate, and more demanding in structure and heat control. Some materials work better than others. Hydrogen-rich materials can help against certain kinds of radiation. Water can help too, which is useful because a ship already needs water. If you are living on the moon or Mars one day, you might bury a habitat under soil or rock and get a lot of shielding that way. But a starship does not have that option in the same easy sense. You cannot casually surround an interstellar vehicle with the equivalent of a hill and still pretend the propulsion problem stays the same. And there's another complication that makes shielding less simple than people think. More material is not always a clean solution, because when very high-energy particles hit dense shielding, they can produce cascades of secondary particles. So it's not just about making the wall thicker. It's about what the wall is made of, how the layers are arranged, how much mass you can afford, and what kinds of radiation you are trying to defend against. This is not like putting on a thicker winter coat. It's a complex trade-off between protection, mass, and the new hazards created by the shield itself. Then solar storms make the situation even worse. Galactic cosmic rays are the slow, constant threat. Solar particle events are the sudden threat. A major solar storm can hit the crew with a large radiation dose over a short period. That means the ship can't just have general shielding. It may need storm shelters, heavily protected internal spaces where the crew can hide during dangerous events. That sounds reasonable until you follow the design implications. Now you need nested protection, a more heavily shielded core inside the ship, routing plans, emergency procedures, and enough mass in exactly the right places to keep those shelters effective. Again, the mission gets larger, heavier, and more complicated. And this is why radiation is so destructive to the interstellar dream. It doesn't have to kill the crew in one dramatic event to ruin the mission. In fact, the more realistic danger is that it slowly degrades the crew over time. Maybe cancer rates go up. Maybe fertility is affected. Maybe the nervous system is damaged slowly enough that cognition declines across years. Maybe blood vessels, tissues, and organs accumulate injuries that are hard to reverse. The ship may still be flying, the lights may still be on, life support may still be running, but the people inside are getting worse. That kind of failure is especially dangerous on a very long mission because it doesn't look like a single disaster you can isolate and repair. It looks like biology wearing down under a permanent particle storm. And human beings did not evolve for that. Our species evolved under air, under weather, under a magnetic field, under the protection of a thick atmosphere. Once you leave that environment, radiation becomes one more way the universe keeps adding pressure to every weak point in the mission. So now the picture is even severe. The ship is already too heavy, too energy hungry, too biologically fragile, and too dependent on systems that must not fail. Radiation adds another permanent cost. More shielding, more mass, more medical risk, more long-term damage. And the next problem is just as brutal, because even if you somehow protect the crew from radiation, high speed creates another threat that turns ordinary matter into a weapon. The faster you try to go, the more empty space stops being safe. That sounds backward because space looks empty. When people think about collisions, they picture crowded places. Traffic, debris fields, asteroid belts packed with rocks. Interstellar space does not look like that. It looks like nothing, but almost nothing is not the same as nothing. And once your ship is moving at extreme speed, that difference becomes deadly. The space between stars still contains matter. There's gas, dust, plasma, and scattered larger particles. The density is very low, yes, but the distance you are trying to cross is enormous. Over that kind of distance, even a thin spread of material stops being harmless. If you move slowly enough, the risk stays relatively manageable. If you try to move at the kind of speed humans would need for an interstellar trip, the whole picture changes. A single tiny particle can hit with enough energy to do serious damage. This is another place where human intuition fails. A grain of dust sounds trivial. A few milligrams sounds like nothing. On Earth, that's something you would wipe off a table, but speed changes the meaning of mass. At very high velocity, even tiny objects carry huge energy. And once you start talking about a ship moving at something like 10% of light speed, those small particles are no longer a nuisance. They become impacts with extreme local violence. The key point is simple. When speed goes up, impact energy rises very fast. So the danger is not mainly about hitting large objects, though that would be catastrophic too. The danger is that at high enough speed, even very small things stop acting small. A dust grain doesn't gently tap the hull. It strikes with enough force to generate heat, plasma, fragmentation, and damage concentrated into a tiny area. One hit might not destroy the whole ship, but repeated hits over years or decades become a serious engineering and survival problem. And this is not only about punching a hole through metal. At those speeds, an impact can vaporize material, blast fragments inward, and damage layers beyond the point of contact. The event can produce what engineers call spallation, where material breaks off from the inside after the shock moves through the wall. So even if the outside doesn't look completely shattered, the structure may still be getting damaged in ways that add up over time. This is not a simple "can the hull take a hit" question. It becomes a problem of energy dissipation, repeated erosion, and protecting the living volume from countless violent micro-events. Current spacecraft already use shielding ideas to deal with impacts. One common concept is the Whipple shield. Instead of relying on one thick wall, you use a thin outer layer that breaks up a particle before the fragments reach the main hull. That works well for micrometeoroids and orbital debris at the kinds of speeds spacecraft deal with today. It's a smart solution for current missions, but the important phrase there is "for current missions." Interstellar travel at a large fraction of light speed pushes the threat far beyond the regime where we have real operational answers for crewed systems. That matters because the faster you go, the more your forward-facing side becomes a permanent danger zone. The front of the ship is no longer just the direction of travel. It becomes the part taking the worst punishment continuously. Every bit of dust in your path is now a potential impact event. Every design choice has to respect that. You may need sacrificial forward shielding, thick protective layers, specialized geometry, and probably systems meant to absorb damage over time without letting it reach the habitat behind them. That means more mass again, and mass, as we have already seen, poisons the rest of the mission.
Then people ask the obvious question: can't the ship just detect hazards ahead of time and avoid them? In some cases, maybe. Larger objects might be detectable. Radar, LiDAR, or other sensing systems could help with some threats. But this answer gets weaker the faster the ship moves. At extreme velocity, reaction time collapses. Even if you detect something, you may not have enough time to respond meaningfully. And many of the most dangerous particles are tiny enough to be hard or impossible to track at useful range before impact. That means the ship cannot rely on seeing everything and steering around it. It would need a mix of sensing, prediction, shielding, and maybe more speculative defenses like particle or plasma deflection systems. But every one of those adds more hardware, more complexity, more power demand, and more mass. Once again, the solution does not remove the problem. It adds another layer to the growing burden of the mission. And the deeper issue is that the threat is built into the speed itself. If you stayed slow, the collisions would be less violent, but then the travel time becomes useless for humans. If you go fast enough to make the mission meaningful within a lifetime, the medium you are crossing becomes much more dangerous. So now the ship is trapped between two bad options. Slow travel makes the mission too long for human life. Fast travel turns ordinary particles into high-energy impacts. That is why this section matters so much. It shows that high speed is not just hard because of propulsion. High speed also changes the environment around the ship. Deep space does not need to be crowded to be dangerous. It only needs to contain a small amount of matter, and it does. Once velocity gets extreme, that is enough. And the effect on design is severe. The ship cannot just be fast, it has to survive being fast. That means protecting the forward structure, protecting the crew behind it, accounting for cumulative damage, and planning for impact physics we have not solved for crewed interstellar systems. The front of the vehicle becomes a permanent defensive problem. The hull is no longer just a shell around the habitat. It becomes armor under constant threat. This is why the travel time solution keeps creating new disasters. You need huge speed to get humans across interstellar distance in any meaningful time. But huge speed makes dust dangerous, small debris lethal, and the entire route physically more hostile. The exact thing that makes the trip possible on paper makes the journey harder to survive in reality. And once that sinks in, another hidden problem gets much harder to ignore. Because even if you somehow survive the trip out, even if the ship stays intact and the crew stays alive, there is still one question that wrecks a lot of optimistic ideas. Getting there is not enough, because if you cannot slow down, you never really arrive. Getting there fast is not enough, because if you cannot slow down, you do not actually arrive. This is one of the biggest hidden failures in casual talk about interstellar travel. People say, just build a ship, make it incredibly fast, point it at another star, and send it. But that only solves part of the trip, and not even the most useful part. If a ship reaches another star system at a major fraction of light speed and does nothing to reduce that speed, it does not enter the system in any meaningful way. It blows through it. A planet, a moon, an atmosphere, a possible biosignature,
All of it flashes by at such speed that the mission becomes little more than a very expensive pass. That is why a flyby is not arrival. Reaching the target system and being able to operate there are two different things. If you want humans to study a planet, enter orbit, land, build anything, or even just spend time making observations that matter, the ship has to slow down. It has to get rid of most of the speed that made the trip possible in the first place. And that is where the problem becomes much more severe, because deceleration is not some minor final step. It is as hard as acceleration. That changes the whole shape of the mission. A lot of optimistic arguments quietly treat the trip like a one-way speed problem. Just solve the outbound acceleration and you're basically done. But a useful mission needs acceleration and deceleration. In broad terms, that means the energy burden roughly doubles. And in many realistic designs, it becomes worse than that because of mass ratio. If your ship carries propellant to slow down later, then that braking propellant has to be accelerated during the first part of the mission. So now you're spending energy to carry the fuel that will later be used to undo the speed you paid so much to gain. This is where the mission starts looking almost absurd. The first half of the trip is no longer just about pushing the ship. It's also about pushing the means to stop the ship. And the second half only works if all of that braking capability is still intact after decades of exposure, wear, and accumulated risk. So the idea that a star mission is half solved once you can go fast enough is deeply misleading. Once you can go fast enough, the real difficulty may only be starting. That is why beamed propulsion gets so much attention. It sounds like a way out. If you can push the ship from a distance with lasers or some other external energy source, then maybe you don't have to carry all the reaction mass on board. For tiny probes, that idea has real appeal. A very small payload can be pushed much easier, and if it only needs to do a fast flyby, the mission is at least conceptually cleaner. But human missions are not tiny probes. The mass is vastly larger, the structure is vastly more complex, and the crew cannot accept a one-way high-speed pass as success. So for a human-scale payload, beamed propulsion shifts the problem instead of erasing it. You still need an enormous energy system back home. You still need the beam to stay accurate over extreme distances. You still need hardware capable of surviving the acceleration. And then the hardest question returns. How do you slow down at the other end? A laser system in the solar system can push you outward, but it can't easily get in front of you when you arrive and break you unless the destination system already has comparable infrastructure waiting. And if you need another civilization, or your own civilization centuries earlier to build huge braking systems around another star before the mission can work, then the mission is no longer about one ship. It's about constructing a huge interstellar support network first. People have proposed ideas for that too. Magnetic sails, drag against the interstellar medium, interaction with stellar winds, all of these concepts exist on paper in some form. They're interesting and they matter scientifically, but for human-scale vehicles, they remain deeply speculative and extremely severe in their requirements. The scales are enormous. The structures could be enormous. The timelines are enormous, and the uncertainty stays high. These are not mature operational solutions. They are ways of showing that physics might allow some braking method in principle. That is very different from having a workable mission design. And this is where the problem finally exposes its full size. You start by asking, can we build a starship? That sounds like a vehicle question. Then braking forces you to ask a much bigger question. Can we build the energy and transmission infrastructure needed to control that vehicle across interplanetary or even interstellar distances? Now the mission is not one machine. It is a civilization-scale energy architecture focused on one act. The ship becomes just a visible tip of a much larger system. That matters because it destroys the simple fantasy version of the idea. The fantasy version is a single great vessel leaving home under its own power and reaching another sun through courage and engineering. The real version is far heavier, far more dependent on prior infrastructure, and far less elegant. It is not one heroic machine. It is a moving world tied to extraordinary support requirements, trying to control immense velocity without the safety nets that normal space missions depend on. And stopping is where that fantasy usually collapses, because once you admit braking is essential, all the loose optimism starts disappearing. The ship is not just a fast object. It is a self-contained habitat that has to survive acceleration, survive cruise, survive impacts, survive radiation, keep its crew alive, and then shed almost all of its speed without destroying itself or requiring impossible amounts of additional mass. That is a much harder sentence than go to another star. At that point, leave the solar system no longer sounds like a bold next step in exploration. It starts sounding like trying to move an artificial world across lethal distance and then place it gently inside another stellar system with no room for major failure. The speed problem was already terrible. The stopping problem makes it much worse because it proves the ship cannot just be fast. It has to be controllably fast over an entire mission architecture that stretches beyond any normal concept of transportation. And once that is clear, the next pressure point gets even darker, because even if you somehow accelerate, protect the crew, survive impacts, and somehow break at the far end, one more enemy keeps growing the whole time, and that enemy is time itself. Time is not just part of the trip, it becomes one of the main things trying to kill the mission. That is easy to miss because people usually think about space problems in physical terms: fuel, engines, radiation, shielding, mass. But human missions are lifetime bound. That changes everything. A robotic probe can be called a success if it works for 20 years. That is a fantastic result for a machine. For humans, 20 years is not some amazing bonus. It is just a medium-length mission if you're talking about interstellar travel. And that is the first hard reality here. If the crew cannot reach the destination inside a human lifetime, then you're forced into one of two options. Either the ship becomes a generation ship, where multiple generations live and die during the voyage, or you rely on suspended animation, which people usually call cryosleep. One of those is a civilization experiment. The other is not a real capability we currently have. That is why time is so destructive to this whole idea. The longer the mission lasts, the less it behaves like transportation, and the more it behaves like trying to preserve a functioning human system against decay. And decay is everywhere. Machines wear out, materials fatigue, seals weaken, electronics age, sensors drift, components fail. We do not build machines that run cleanly for centuries on their own. Even our strongest systems on Earth, bridges, ships, reactors, power grids, all require inspection, maintenance, replacement, and industrial support behind them. They survive because an entire civilization keeps repairing them. A starship would not have that safety net. It would have to carry the ability to diagnose its own failures, fix them, replace damaged components, recycle materials, and rebuild internal systems over and over again. And that means it cannot just carry spare parts, because spare parts run out. It has to carry tools, manufacturing systems, raw material recovery systems, technical knowledge, trained operators, and enough redundancy to survive mistakes and failures while repairs are happening. In effect, the ship has to bring part of an industrial base with it. And this is where the problem becomes much worse than people expect. Reliability over centuries is not just a bigger version of reliability over years. It's a different category of challenge. A machine that lasts 10 years is one thing. A machine that supports human life for 100 years or 200 or longer without outside rescue is something else entirely. The difficulty does not rise smoothly. It rises sharply because every subsystem becomes a long-term liability. The life support system has to keep working. The power system has to keep working. The repair systems have to keep working, and the systems used to repair those systems have to keep working too. Then software and knowledge start becoming a threat. Long missions are not only threatened by broken metal and worn bearings. Data can be corrupted. Storage media can degrade. Hardware becomes old. Interfaces fail. Software environments become fragile. We already know that on Earth, even in normal timescales, digital systems need updates, migration, maintenance, and people who understand them. Stretch that over generations and the problem gets very serious. A system can remain physically present but become unusable because the knowledge around it erodes. And that erosion is not only technical. A generation born aboard the ship may not preserve the same engineering discipline, educational standards, or mission priorities as the people who launched it. The failure mode is not always one sudden accident. It can be drift, slow drift in technical competence, slow drift in values, slow drift in how procedures are followed, how systems are understood, how seriously maintenance is taken, how the mission is explained. A ship can die because nobody knows enough to keep it alive, or because the reasons for keeping it alive stop mattering to the people inside it. That is why cryosleep sounds so attractive. It seems like a clean way around all this. Put the crew into suspended animation, let the ship run mostly by itself, wake everyone up when you arrive, problem solved. But that is not a solved technology. It's a story people tell because it removes complexity in one sentence. Current science does not offer reversible whole-body human cryopreservation that preserves a living person through long durations and returns them safely to normal function. Freezing and rewarming tissue damages cells. Ice formation can destroy structure. Blood flow problems, molecular stress, and organ damage are major barriers. So cryosleep is not a practical escape hatch. It's another unsolved problem being used to patch over the first unsolved problem. And this is why time itself becomes such a brutal enemy. The longer the mission lasts, the less it belongs to the people who started it. At some point, the ship is no longer our mission in any meaningful sense. It belongs to descendants, or to people not yet born, or to automated systems maintaining a goal that no living human chose firsthand. That changes the mission psychologically and socially. If the trip takes thousands of years, the launch civilization may not even exist by the time the ship is still halfway there. The people who made the decision are gone. The language they spoke may be gone. The culture that justified the mission may be gone. The destination may still be far ahead, but the original meaning of the voyage has already died behind it. That is one of the darkest parts of this entire subject. The ship does not just have to survive physics, it has to survive irrelevance. It has to carry a purpose forward through timescales that break human continuity. And humans are not built for that. We are finite beings trying to create a machine that can preserve function, knowledge, discipline, and intent over spans of time that swallow institutions whole. So when people say interstellar travel is only a matter of better engineering, this is one of the strongest reasons that is not true. Engineering is part of it, but time expands every weakness. It wears down hardware, information, culture, trust, and meaning. It turns the mission from a voyage into a test of whether anything human-made can resist drift long enough to stay coherent. And once time breaks the idea of support, continuity, and mission identity, the next problem becomes even harder because distance does not just stretch the trip, it also destroys the link back home. And when that happens, Earth stops being mission control and turns into something much more distant than people expect. Distance does not just make rescue hard, it makes support almost meaningless. That is one of the biggest shifts people fail to take seriously. In normal spaceflight, even when missions are dangerous, Earth is still part of the system. Ground control can monitor data, send instructions, help troubleshoot, coordinate experts, and support the crew continuously. Even with delays, there's still a real connection. But that model starts breaking down long before interstellar travel, and by the time you're talking about another star, it is gone. Radio signals move at light speed, and light speed is the fastest anything can travel. That sounds impressive until you remember how large space really is. A message from Mars can take anywhere from about 3 to 22 minutes one way, depending on where Earth and Mars are in their orbits. For Pluto, you're dealing with delays measured in hours. That's already enough to make real-time control impossible. A spacecraft out there is not being flown like a drone. It has to wait. Earth has to wait, and everything becomes slower, less flexible, and less responsive. Now, push that out to the nearest stars. If a ship is 4 light-years away, one message takes about 4 years to arrive. A reply takes another 4 years to come back. That means even the simplest exchange takes more than 8 years round trip. That is not communication in the normal sense anymore. That is sending history back and forth. You can't ask a question during a crisis and get help while the crisis still exists. You can't have a live discussion. You can't gather a team on Earth, review the problem, and talk the crew through it. By the time the answer arrives, the people who asked the question may be dead, the problem may be gone, or the ship may already have changed course in some irreversible way. That destroys one of the most comforting assumptions in all of space travel, the idea that Earth is always there to help. On an interstellar mission, emergencies become local permanently. Navigation corrections are local, medical crises are local, software failures are local, habitat failures are local, psychological breakdowns are local, conflicts inside the crew are local. Decisions about authority, justice, education, resource allocation, all of it is local. Earth cannot function as mission control because mission control is too far away to control anything that matters in real time. And that changes the design of the mission completely. You're no longer sending a crew that operates machinery under distant supervision. You're sending a system that must govern itself completely. That means the people on board can't just be astronauts in a usual sense. They need expertise across medicine, engineering, ecology, leadership, and probably law and conflict resolution too. The ship has to contain enough knowledge and institutional stability to replace what Earth normally provides. That is why the word crew starts becoming too small. A crew runs a vehicle. A starship carrying humans has to do much more than that. It has to preserve a functioning human system. It has to train new people, settle disputes, maintain standards, protect knowledge, make legitimate decisions, and survive changes in leadership and culture without losing the ability to stay alive. In plain terms, you're not just sending operators, you're sending the beginning of a society. And once you see it that way, communication delay becomes more than a technical issue. It becomes a psychological and cultural one too. Messages from Earth would not feel like normal contact. Over long enough timescales, they would feel like archaeology. News would arrive years late. Personal messages would arrive from people who may already be dead by the time you hear their voices or read their words. Your reply would be aimed at a future you cannot see. The people who answer may not be the same people or the same culture or even speak the language in quite the same way. That weakens morale in a very direct way. The emotional link to home starts breaking apart. The ship may still remember Earth as its origin, but the living connection fades. The launch generation dies. The generations after them grow up with a very different relationship to the mission. Earth becomes less like home and more like a distant historical source. At some point, the people on board are no longer emotionally anchored to the civilization that sent them. They're just living inside a closed world, receiving delayed signals from a place that may no longer understand them and that they may no longer feel responsible to. That matters because support is not only technical, it's also moral. On Earth, institutions keep missions legitimate. Governments fund them, agencies oversee them, laws shape them, cultural values justify them. But at interstellar distances, command weakens until it effectively disappears. You cannot supervise a society across a gap where messages take years each way. You cannot meaningfully enforce policy. You cannot rescue a crew. You cannot patch the ship the way you patch networks or update satellite constellations. Once it leaves, it leaves. And that's the deeper point here. Interstellar distance kills command, not just conversation. It removes the assumption that a mission can stay tied to the civilization that launched it. That degree of autonomy is not some nice advanced feature. It's another major source of risk. The ship has to survive not only hardware failures and biological stress, but also the complete absence of real-time oversight from home. So now, the mission is even harder to defend. It has to be self-sustaining, self-repairing, self-governing, medically capable, socially stable, and psychologically durable, all while knowing that help from Earth is too slow to matter. And once that isolation becomes permanent, another threat becomes unavoidable. Because even if the hardware holds together, even if the rules are clear, even if the ship can function technically, the people inside still have to endure confinement on a scale no human society has truly tested. The hardware doesn't have to fail first. People can fail first, and for a human mission, that may be even more dangerous. That point is easy to underestimate because psychology sounds softer than engines, shielding, or life support. It sounds secondary, but it's not secondary at all. We already know from real environments on Earth that confinement changes people. Submarines, polar stations, isolation experiments, and long-duration missions in orbit all show the same basic pattern. Small tensions grow larger. Repetition wears people down. Sleep gets disrupted. Motivation drops. Anxiety and depression can appear. Cognitive fatigue builds. Minor conflicts that would be manageable in ordinary life can become serious when there is no real escape from the group. And all of that is happening in situations where people still know a few important things. They know there is an end date. They know there is a larger world outside.
They know rescue or rotation is possible, at least in principle. They know Earth is still present in real time as a social and institutional support system. That does not remove the stress, but it limits it. The crew can tell itself that the confinement is temporary. That matters a lot. Interstellar confinement strips even that away. There is no rescue date that feels close enough to matter. There is no horizon. There is no fresh air. There is no landscape, no changing city, no real outdoors, no meaningful contact with a wider human world. The environment does not open up. It stays bounded by walls, systems, corridors, routines, and the same people. Even if the ship is large by spacecraft, and all of that is happening in situations where people still know a few important things. They know there is an end date. They know there is a larger world outside. They know rescue or rotation is possible, at least in principle. They know Earth is still present in real time as a social and institutional support system. That does not remove the stress, but it limits it. The crew can tell itself that the confinement is temporary. That matters a lot. Interstellar confinement strips even that away. There is no rescue date that feels close enough to matter. There is no horizon. There is no fresh air. There is no landscape, no changing city, no real outdoors, no meaningful contact with a wider human world. The environment does not open up. It stays bounded by walls, systems, corridors, routines, and the same people. Even if the ship is large by spacecraft standards, it is tiny by human standards. It is not a world in the full sense. It is a managed enclosure. That changes the psychological pressure completely. People are not just living in a hard environment, they are living in an environment that never stops being hard. The normal outlets humans use to reset themselves, movement through larger spaces, contact with nature, social variety, privacy at a meaningful scale, cultural change, novelty that is not manufactured, all of that becomes limited or artificial. Over years, that matters. Over decades, it may become one of the central threats to the mission. And this is why group dynamics stop being a side issue and become part of mission physics. On Earth, if a team has a serious conflict, it can damage productivity, safety, or morale. On a starship, it can damage survival. A fight, a breakdown in trust, a split into hostile factions, a power struggle, a destructive ideology, a cult, an authoritarian system, a conflict between generations. None of those are just social problems sitting beside the engineering. They are engineering problems now. A socially unstable ship is a technically unstable ship. That is the part people usually resist because they want to keep technical and human issues separate, but they are not separate here. If the people maintaining life support stop trusting each other, that affects life support. If governance fails, that affects resource allocation and safety procedures. If part of the population rejects the mission's purpose, that affects maintenance, education, discipline, and long-term continuity. Social stability becomes as fundamental as whole integrity. A broken society inside the ship is not something the mission can simply work around. It is a direct path to failure. Then there's the standard reply. Just select the right people. Pick the best, smartest, most disciplined, most psychologically resilient individuals. Of course, that would help. Selection matters, training matters, screening matters. But it does not solve the problem. No screening system can fully predict how human beings will behave across decades under conditions no population has ever lived through before. People change, relationships change, power changes people. Stress changes people. Isolation changes people. And no selection process can fully account for the generations that come later, because those people were not selected at all. They were born into the ship. That makes generation missions even more unstable psychologically. The first crew may be highly trained volunteers. Their children are not volunteers in the same way. Their grandchildren even less so. Later generations may not accept the mission's values. They may not accept the authority structures that were designed to preserve order. They may not even agree that the destination matters enough to justify the restrictions of shipboard life. And this is where one of the oldest assumptions about space travel starts breaking apart. People often assume the technology is the hard part and the humans are just the passengers. That may be exactly backward.
The ship can be technically excellent and still fail because the human system inside it fails. Or, to say it more clearly, the humans are not separate from the spacecraft. They are one of its most fragile subsystems. That is what makes this section so uncomfortable. It says that even if you solve the giant visible problems, propulsion, shielding, energy, life support, autonomy, you still may not have solved the mission, because the mission has to survive the human mind under pressure no civilization has ever really tested. The hardware can keep running, and the people can still stop functioning as a stable collective. And once you accept that, the next step becomes even harder to ignore, because a multi-generational ship is no longer just a vehicle carrying stressed people. It becomes a closed, artificial civilization, and that brings a whole new layer of risks that go far beyond normal spaceflight. A generation ship is not really a ship anymore. It's a small civilization that has to stay healthy for longer than most human systems ever survive. That changes the problem completely. Once the mission is longer than one lifetime, you're no longer talking about astronauts going somewhere. You're talking about children being born, growing up, having children of their own, and living their entire lives inside one closed machine. At that point, biology, sociology, education, and engineering all become the same problem. The vehicle is no longer just carrying people. It's carrying a whole human continuity that has to remain functional without outside support. Start with population size, because that sounds simple, and it is not. If the population is too small, you run into serious risks very quickly. Inbreeding becomes a concern. Genetic diversity becomes harder to preserve. A few deaths, accidents, or fertility problems can destabilize the whole system. Certain critical skills may be held by too few people. Social life becomes fragile because the number of relationships, families, and roles is too limited. A very small population is easier to launch, easier to feed, and easier to house, but it is also easier to break. Then go in the other direction. If you make the population larger to improve genetic resilience and social stability, the engineering burden rises sharply. More people means more air, more water, more food, more waste, more heat, more medical care, more living space, more education, more governance, more equipment, and more redundancy. The habitat mass rises, the agricultural system grows, the recycling system grows, the energy demand grows. So there is no easy answer. Too few people and the society is fragile. Too many people and the ship becomes much harder to build and move. The mission turns into a balancing act between biology and engineering, and both sides punish mistakes. Then there's ecology, which may be even less forgiving. A generation ship cannot survive on stored supplies alone if the mission lasts centuries. It needs an internal living system that keeps working. Crops have to grow. Water has to be recycled. Air chemistry has to stay within safe ranges. Waste has to be processed. Microbes have to remain useful where you need them and under control where you do not. Nutrients have to cycle again and again without slowly falling out of balance. That sounds like something you could solve with good planning until you look at real ecosystems. Real ecosystems are complicated. They are full of feedback loops, hidden dependencies, and nonlinear behavior. Small disruptions can become large disruptions. A pest outbreak could damage food production. A fungal disease could spread through crops. A microbial change could affect waste processing or air quality. A trace gas imbalance could build slowly and become dangerous before anyone fully understands what is happening. On Earth, ecosystems fail locally all the time, and the planet absorbs the damage because the biosphere is huge and redundant. A starship does not get that luxury. There is no backup forest, no backup ocean, no backup atmosphere. If the internal ecology starts slipping, the crew has nowhere else to go. And then governance stops being theory and turns into survival hardware. On Earth, bad governance can ruin lives, destroy economies, start wars, or collapse states. On a generation ship, it can also kill everybody directly. Someone has to decide how resources are used. Someone has to enforce safety rules. Someone has to manage conflict, crime, education, medical triage, labor, maintenance, and emergencies. That is already hard in a normal society. In a closed habitat where every major system is mission critical, it becomes much more dangerous. Questions that sound abstract on Earth become practical immediately. Who gets authority and why? Can later generations reject the mission? Can someone opt out of life inside the system? What happens if a group decides the destination is not worth the sacrifice? What happens if people refuse population controls, work assignments, or technical education? What happens if the leadership becomes corrupt, cruel, incompetent, or simply weak? On a generation ship, failed governance is not just tragic, it can be terminal. Then culture drift enters the picture, and this may be one of the hardest parts to control. Over centuries, people do not just preserve information automatically. They reinterpret it, they simplify it, they turn procedures into traditions, then traditions into myths. If education is not maintained with extreme discipline, the original mission can slowly stop making sense. Manuals become less important than stories. Technical reasons become moral slogans. The destination can turn into an article of belief, a source of resentment, or both. Think about what it means to be born on that ship. You never saw Earth. You never agreed to the voyage. Your whole world is metal, systems, restrictions, maintenance, and inherited duty. Then someone tells you that your life exists to continue a mission started by dead ancestors for a destination you may never see. That is not a minor philosophical issue. That goes directly to obedience, legitimacy, and social stability. Why should later generations keep sacrificing for a goal they did not choose? If they stop believing in it, the mission weakens. If they turn it into dogma, the mission may survive in form, but drift away from the knowledge needed to keep it working. And this is why the phrase human mission to another star becomes misleading at this stage. It sounds like exploration. It sounds like a longer version of a normal expedition. But that is not what a generation ship really is. It's an attempt to create a closed civilization under conditions tighter than almost any human society has ever experienced, and then expect that civilization to remain healthy, lawful, technically competent, biologically stable, and purpose-driven across timescales longer than many nations survive. That is an enormous demand. It's not just a demand for better engineering, it's a demand for stable genetics, stable ecology, stable governance, stable education, stable culture, and stable legitimacy, all inside one artificial environment with no real escape. In other words, the ship stops being transport and starts becoming a prison world gamble with very advanced machinery. And even if you somehow accept all of that, even if you somehow keep the society alive and functioning, one more brutal possibility is waiting at the far end. Because after all that cost, all that time, and all that risk, the destination itself may still fail you. After everything the mission demands, there is still no guarantee the destination solves anything. That is one of the most brutal parts of the whole argument. People often talk as if the hard part is the journey, and once you survive that, the reward is waiting for you at the other end. But with interstellar travel, the destination is not a promised rescue. It might just be another problem. You can spend extreme amounts of energy, mass, time, and human effort getting there, and still arrive at a place that doesn't let humans live outside the ship. Start with the information problem. Even with better telescopes and better exoplanet science, what we know about distant worlds is limited. We can often estimate orbital period, sometimes we can estimate size, sometimes mass. In special cases, we can get hints at atmospheres, temperature ranges, or possible chemical signatures. That is powerful science, but it's not detailed local knowledge. It's not the kind of information you'd want before committing a generation civilization to a one-way journey. A planet can look promising from very far away and still be a terrible place for human life. Spectroscopy might hint at certain gases, but that doesn't tell you whether the atmosphere is breathable, stable, or full of dangerous chemistry. A planet might sit in the so-called habitable zone and still be sterile, dry, geologically dead, unstable, or exposed to severe radiation. It could be tidally locked in a way that creates brutal temperature extremes. It could have an atmosphere that exists but is unhelpful to us. It could have water and still be hostile in every way that matters to humans. This gets even more serious because the nearest stars are not sun-like stars. The closest systems, including Proxima Centauri, are red dwarfs. Red dwarfs are common and long-lived, which sounds encouraging at first, but many of them are also active, especially in ways that can be bad for nearby planets. Their habitable zones are close in because the stars are dimmer than the sun. That means a planet can be in the nominal habitable zone and still be much more exposed to stellar activity than Earth is.
Take Proxima b as the classic example people point to. It sits in the star's nominal habitable zone, which sounds exciting, but that phrase can be very misleading. Habitable zone mainly means a place where liquid water might be possible under some conditions. It does not mean the planet is Earth-like. It does not mean the atmosphere is safe. It does not mean the planet has a magnetosphere or mild weather or stable oceans or biological protection. And because the planet is so close to its star, it may face strong flare exposure and tidal effects that make the environment much harsher than the simple label suggests. That is the danger of optimistic language in this field. A promising exoplanet is not a future home in any useful sense. It is a target with incomplete data. For a robotic mission, incomplete data is acceptable. You send instruments, take measurements, learn more. For a human interstellar mission, incomplete data is much more serious. You're not sending a probe that can fail cheaply. You're sending a living society toward a place that may not support it. And even if the ship arrives successfully, the planet itself may still be unusable. The gravity could be too high for long-term human health, or too low to keep the body functioning well across generations. The atmosphere might be too thin, too thick, too toxic, or chemically unstable. The radiation environment might be severe because there is no useful magnetic shield. The surface chemistry could be corrosive or poisonous. There may be no accessible biosphere, no easy agriculture, no familiar ecology to work with, and no simple way to live outside artificial systems. At that point, the starship does not stop being essential. It remains the habitat. After an impossible journey, after solving propulsion, shielding, time, autonomy, medicine, governance, psychology, and survival, you may still be living inside the ship because the world outside does not actually want you there. You have not reached a new Earth. You have reached another place where your machine is still the only island of life. And then colonization becomes its own giant wall. People often say travel to another star and settle another star as if the second part naturally follows from the first. It does not. Settlement may be even harder. You need local energy, you need shelter, you need mining, manufacturing, medical systems, agriculture, construction, waste handling, transport, and adaptation to unfamiliar conditions. You need to build an industrial base from almost nothing, while preserving the lives of the people who arrived. If the environment is only partly suitable, the settlement remains dependent on artificial habitats. If the environment is highly unsuitable, the mission becomes permanent life inside machines parked in another star system. That means travel does not end dependence on the spacecraft. It can extend it indefinitely. The ship, or a network of habitats descended from it, remains the true life support system. The new star does not free you from engineering. It may trap you deeper inside it. And that leads to the most painful possibility in this whole section. After all the sacrifice, all the mass, all the energy, all the generations spent surviving the trip, the destination may still fail in exactly the same way the journey failed. It may demand more infrastructure, more resilience, more biological adaptation, and more luck than humans can realistically bring. In that case, the mission does not end in liberation. It ends in continued dependence under a different sun. That is the final insult in this part of the argument. The stars are not just far away, they are uncertain. You are not traveling toward a guaranteed refuge. You are traveling toward a place that might turn out to be only slightly less deadly than the space between here and there. And if that is true, then the journey is not simply difficult, it may be strategically irrational for humans in the first place. And that pushes the whole argument toward its hardest conclusion. Because once you accept that physics may allow interstellar travel in the abstract, while human bodies, societies, and civilizations still cannot carry it out in any realistic way, the real distinction finally becomes unavoidable. Nothing in known physics clearly says matter can never move from one star to another, but that is not the question that matters for humans. This is where people often hide behind a technically true sentence. They say interstellar travel is not forbidden by physics. That is correct in a narrow sense. The laws of physics do not place a sign in front of the stars saying entry impossible.
But that truth can be very misleading, because physics also does not forbid many things that are still far beyond what a real civilization can actually do. Physics does not forbid enormous artificial habitats in orbit powered by giant energy systems. Physics does not forbid structures on scales much larger than anything we have ever built. The issue is not whether the universe gives abstract permission. The issue is whether a species like ours, with short lives, fragile bodies, limited budgets, and machines that wear out, can actually carry the burden. That distinction matters more than almost anything else in this whole discussion. If you talk only at the level of pure physics, the answer sounds more open. If you talk at the actual human reality, biology, industry, economics, psychology, governance, reliability, and time, the answer becomes much harsher. The stars are ruled out by not one simple law. They are ruled out by the total weight of everything a human mission would require all at once. And once you separate those two levels clearly, a more realistic path starts to appear. We can send machines much sooner than people, and probably much more effectively. That is not a weak fallback. That is the scientifically serious answer. A tiny probe pushed by beamed energy fits the scale of the problem far better than a crude habitat. An advanced autonomous explorer makes far more sense than a ship carrying families, farms, hospitals, and systems. A machine can be stripped down to function. It can accept a one-way trip. It can accept long silence. It can accept risk levels that would be unacceptable for people. That difference is not a small advantage. It changes the entire mission architecture. A wafer-scale probe does not need oxygen. It does not need food. It does not need shielding like a city. It does not need surgery, schooling, law, governance, or emotional stability. It does not care if the trip takes decades. It does not care if the destination turns out to be hostile, because gathering data may still count as success. A machine can be useful under conditions that would make a human mission irrational. This is why the real sentence that changes everything is simple. Humans are the expensive payload. That is the core of the argument. The problem is not moving matter across interstellar distance. The problem is moving a very specific kind of matter, living, conscious, social, vulnerable matter, and keeping it healthy the entire time. The moment you insist on humans on board, the mass goes up, the shielding goes up, the medical burden goes up, the life support burden goes up, the governance burden goes up, the ethical burden goes up, and the mission stops looking like exploration and starts looking like an attempt to transport a fragile society through a hostile environment for impossible length of time. That is why almost every serious obstacle in this script becomes dramatically worse the moment humans enter the picture. Distance gets harder because lifetimes are short. Energy gets harder because habitats are heavy. Radiation gets harder because bodies are delicate. Collision risk gets harder because the ship cannot just be a hardened instrument package. Time gets harder because society must survive, not just hardware. Communication gets harder because people need meaning, support, and legitimacy, not just telemetry. Psychology gets harder because minds can break. Ecology gets harder because bodies need whole systems around them. The mission complexity does not rise a little when humans are on board, it jumps by orders of magnitude. And this is why saying we sent probes already misses the point so badly. Of course we can send probes. That is exactly what makes interstellar exploration realistic in one form and unrealistic in another. Machines fit the problem better. They fit the distances better. They fit the energy budget better. They fit the risk better. If humanity ever has a meaningful interstellar presence, the first real ambassadors are probably not going to be flesh and blood crews waving at an alien sunrise. They are much more likely to be instruments, code, robotic systems, autonomous explorers, maybe eventually systems descended from our intelligence that are no longer biologically human in the normal sense. That is not defeat. It is the honest conclusion you reach when you stop mixing human dreams with physical scale. Sending machines first is not a lesser version of exploration. It may be the only version that matches the actual problem. A machine can go where a human cannot, not because machines are more noble or more important, but because they are far cheaper to protect and far less demanding to sustain. And this is where the main claim becomes as hard and clear as it needs to be. Is it absolutely, mathematically, forever impossible for a human to leave the solar system? In the narrowest possible courtroom sense, maybe not. You can always leave room for some future breakthrough, some radical change in technology, some transformation of civilization so extreme that it changes the answer. But if you stay grounded in the reality we actually understand, the reality of energy, mass, shielding, biology, autonomy, psychology, governance, and time, then the answer is effectively yes. Not because the universe is breaking its own rules, not because physics is cruel in some dramatic way, but because the scales involved are so large and the demands of keeping humans alive are so extreme that human passengers become catastrophically impractical. The universe does not have to forbid us directly, it only has to be big enough, cold enough, and demanding enough that carrying human life across it stops making realistic sense. And that leads to the final step in the argument, because once you accept that the stars may still be explored by machines, while biological humans remain effectively trapped inside the solar's domain, then the ending stops being about failure and starts being about a much stranger possibility. The solar system itself may be the only real human ocean we will ever have. For a long time, people talked about the stars like they were automatically our next destination, as if history had a built-in direction. First the moon, then Mars, then other star systems, then everything beyond that. But the more seriously you look at the science, the less that story holds up. The problem is not that space has no future for humans, the problem is that we may have confused reach with destiny. Just because you can see the stars does not mean human bodies and human societies are built to go there. And once you stop forcing that old story, something else becomes clear. The solar system itself is already so large, so rich, and so demanding that it could occupy human civilization for an immense span of time. Earth alone is one world. Then there's the moon, Mars, the asteroid belt, orbital habitats, industrial infrastructure in space, the outer planets, icy moons, Kuiper belt objects, long-term energy systems, closed ecologies, and scientific work across distances that already break normal human intuition. You do not need another star to have a real cosmic future. You already have more frontier than any civilization in history has ever faced. That matters because people sometimes hear the solar system may be enough and think that sounds small or disappointing. It is neither. A civilization spread across Earth, the Moon, Mars, major orbital habitats, resource networks in the asteroid belt, and maybe farther out into the outer solar system would already be larger in scale than anything humans have ever done. The sun's domain is not a small neighborhood. It's a huge structure of worlds, materials, energy, and distance. For biological humans, that may be all the frontier we can realistically use for thousands, maybe millions of years. And that is where the argument stops sounding purely negative. Yes, there is a tragedy in it. The stars remain out there, visible, measurable, real, and yet probably unreachable for us in person. But there is also clarity in that. The stars can still matter deeply without becoming places where biological humans go. They can still be mapped, studied, listened to, and explored by machines. They can still change science, change philosophy, and change how we understand our place in the universe. But inspiration is not the same thing as access. The universe does not promise your species physical entry into every place it can detect. That is a hard idea, but it does not make humanity small in any insulting sense. It makes humanity specific. We are a species built under one star, on one planet, inside one protective environment. We are not general-purpose organisms made for all cosmic conditions. We are Earth-made, sun-bound creatures who became intelligent enough to discover that the universe is far larger than the conditions that produced us. That is not failure. That is the actual situation. And there is something remarkable in that too. We may be limited in where we can go, but not in what we can understand. That may be the deepest shift in this whole topic. The old story says significance comes from physically expanding everywhere. The harder scientific story says significance may come from something else, from understanding reality honestly, even when reality refuses to fit our ambitions. The value of a species is not measured only by how far its bodies can travel. It is also measured by whether it can face scale, danger, and limitation without lying to itself.
And that brings the whole argument to its final point. When you ask why it is impossible for humans to leave the solar system, the answer is not one dramatic barrier, and it is not one missing invention. It is the combined result of distance, energy, mass, radiation, biology, life support, medicine, psychology, ecology, collision risk, governance, autonomy, communication delay, and time. Each problem makes the others worse. The farther you go, the more expensive it becomes to remain human. Not just alive, human. Physically, mentally, socially, and biologically human. That is the real verdict. The universe is not stopping us with a single locked door. It is showing us that the cost of carrying human life across interstellar distance rises so fast in so many directions at once that the idea becomes effectively impossible in any realistic sense. Not because physics hates us, not because exploration was a mistake, but because human beings are not just passengers. We are the fragile, expensive part of the mission. So the final answer is this. Humans can probably build a huge future in space, but that future may remain inside the sun's domain. The stars may belong first to our machines, our instruments, our code, and whatever forms of intelligence come after us. And biological humanity may remain what it already is, a brilliant local species, born in one small protected region of the cosmos, able to see much farther than it can travel. And maybe that is the real ending. The universe is not telling you that movement is impossible. It is telling you that humanity itself is the limit. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.